Back in 1961, NASA engineers calculated something pretty wild. If you wanted to fly directly to the moon without all that orbital assembly stuff, you'd need at least 73.5 meganewtons of thrust. 8 F1 engines. They drew up Nova, worked out the specs, then cancelled the whole thing, because, honestly, they just couldn't build it. The technology wasn't there yet. Here's what's crazy, though. SpaceX's Super Heavy? 33 Raptor engines, producing exactly 73.5 meganewtons. The rocket NASA couldn't build 6 decades ago flew last month. So, what happens when you take a mission profile from the 1960s and run it on hardware that actually works? Let me walk you through what Nova actually needed. Because once you understand the requirements, everything else makes sense. NASA wasn't just dreaming here. Their engineers did real calculations and came up with hard numbers. Direct descent to the moon demanded 73.5 meganewtons minimum thrust, high-efficiency upper stages, and somewhere between 15 to 16 kilometers per second of total delta V. No margin for error. You burn every drop of propellant in one shot. Launch, landing, return. Miss your numbers by even 5% and you're not coming home. They designed Nova with 8 F1 engines to hit these specs. But here's the thing that actually killed it, and it's almost anticlimactic. The first stage was just too damn wide. Couldn't fit through factory doors, couldn't travel on existing roads. They'd have to build entirely new manufacturing facilities, new transport infrastructure, maybe even new launch pads. When you're racing the Soviets to the moon, you don't have time or money for that. Saturn V with Lunar Orbit Rendezvous was cheaper and used existing facilities. Nova stayed on paper, this fascinating what-if representing the absolute edge of what 1960s tech could theoretically do. Now look at Starship's actual numbers. Super Heavy's got 33 Raptor 2 engines. Each one pushes 2.256 meganewtons at sea level. Do the math. That's 74.4 meganewtons total, already exceeding Nova's baseline requirement. But thrust alone doesn't tell you everything. The Raptors burn methane and oxygen, which gives them different characteristics than Nova's kerosene-burning F1s. At sea level, Raptors hit 330 seconds specific impulse versus the F1's 265. That's real efficiency. Each kilogram of propellant produces more thrust for longer. The vacuum variance? They push 380 seconds, which matters hugely during those long translunar injection burns. And here's what really separates this from Nova. These aren't paper engines. SpaceX has fired them hundreds of times. Real test data, real throttling profiles, real reliability numbers from actual operations. That's a completely different starting point than what NASA had to work with. I need to be straight with you about something, though. Starship's dry mass sits around 100 to 120 metric tons. That's considerably heavier than what Nova's upper stage would have been. Stainless steel is cheaper and faster to manufacture than aluminum alloys, but it comes with a weight penalty. This matters enormously because of the rocket equation. Every kilogram of structure eats into your payload capacity or your delta V performance. But the lunar configuration changes everything. You strip out the heat shield tiles, that's 15 tons of ceramic you don't need. Remove the header tanks for Earth landing, the grid fins, all the atmospheric control systems. You're looking at 25 to 30% mass reduction. All stuff that serves zero purpose on a moon mission anyway. Suddenly, you're much closer to Nova's original mass ratios. Let me break down the mission math because this is where it gets real. Earth escape velocity is 11.2 kilometers per second, but launching from the surface through atmosphere adds another 1.5 to 2 kilometers per second in gravity and drag losses. So call it 13 kilometers per second just to get on a lunar trajectory. You coast for 3 days, maybe burn 50 meters per second total for mid-course corrections. Small stuff. Then comes the expensive part. You're screaming toward the moon at 1.6 kilometers per second, and there's no atmosphere to help slow you down. Zero. Every bit of that velocity has to be cancelled with rocket thrust. Powered descent from 15 kilometers altitude burns through 2.5 to 3 kilometers per second when you factor in gravity losses. After you do whatever you came to do on the surface, you need another 2.5 kilometers per second for lunar takeoff and the return trajectory to Earth. Add it all up, and you get 15 to 16 kilometers per second total. The exact same number NASA calculated 60 years ago. Can Starship actually do this? With current specs and a stripped lunar config, the numbers work. Barely. There's almost no margin, which makes me nervous. But this is where SpaceX's whole development philosophy becomes really powerful. They're testing constantly. Raptor 2 beats Raptor 1. Raptor 3 is showing even better numbers in testing. Each generation pushes the envelope higher, and that translates directly to mission capability. This kind of rapid iteration just wasn't possible in the 1960s, when engines were basically handcrafted in small batches. SpaceX cranks out Raptors at volume, and every single engine that fires feeds data back into the design. Problems get caught and fixed across the entire production run. There's another option that could completely change the game, and honestly, it's more practical than you'd think. Starship's cargo bay is massive, 8 meters across, over 17 meters tall, capable of hauling 100+ metric tons to low Earth orbit. That's enough internal volume to fit an entire third propulsion stage with its own engines and tanks. You'd launch this stage inside the cargo bay, where it's protected during the violent ride through atmosphere. Then, once you're in space, you deploy it for the final trans-lunar injection burn. No external modifications to Starship required. The third stage can use vacuum-optimized engines with really high specific impulse. More importantly, it completely changes your Delta-V budget by splitting the mission requirements across multiple stages, each one optimized for what it needs to do. NASA's Nova 8L was a 2-stage design, but they explored 3-stage variants for exactly this reason. The difference now? SpaceX can manufacture this third stage using the same production lines they're already building for Starship. It's not some custom one-off requiring new factories. It's potentially just a smaller, specialized variant of hardware they're making at scale anyway. The propulsion tech itself is where you really see how far we've come since 1961. Raptor throttles from 40 to 100%, giving you precise control during lunar descent, when you're constantly adjusting thrust to fight gravity while managing your descent rate. The engine's response time and smooth throttling make precision landing actually feasible without developing anything new. SpaceX has also been perfecting retro propulsion through hundreds of Falcon 9 booster landings. All that expertise feeds directly into Starship's landing capability. They've got real flight data on engine performance in supersonic regimes, how exhaust plumes behave, control stability through entire descent profiles. This stuff isn't theoretical. What gets me excited about all this is how much of it already exists. The engines are flying, vehicles are testing, control systems are operational. NASA spent decades studying direct ascent missions and left behind comprehensive research on mission profiles, delta-V requirements, operational procedures. That knowledge is sitting in archives ready to use. When Super Heavy lights up those 33 engines and generates 74.4 meganewtons, it's not just matching Nova's paper specs, it's exceeding them with flight-proven hardware. When Starship does its belly flop and powered landing, that's the exact retro-propulsion technique you'd need for lunar descent. Each successful test validates another piece of the direct ascent mission profile. The gap between what Nova needed and what Starship can deliver keeps shrinking. Yeah, mass optimization needs work. The third stage option requires development. Mission procedures need validation. But these are tractable engineering problems, not fundamental technology barriers. NASA couldn't build Nova because the industrial infrastructure and engine technology literally didn't exist yet. SpaceX can build Nova Starship because the hard parts are already solved. What's left is optimization and integration, which happens to be exactly the kind of iterative development SpaceX is really good at. The rocket that was impossible in 1961 isn't just possible today. It's actively being tested with hardware that beats the original specs. So here's what we've figured out. Nova needed technology NASA didn't have. Today, Starship exceeds every one of those specs with hardware that's already flying. The impossible rocket? It's being tested right now. If you got value from this breakdown, hit that like button and subscribe to New Space Review. I want to hear what you think in the comments. Should SpaceX actually pursue direct ascent missions, or is orbital refueling the smarter play? And click that video on your screen about Elon Musk's recently revealed Moon and Mars plans that are making industry experts rethink everything. You'll want to see what's coming. Thanks for watching. See you in the next one.